Hello and welcome everyone to today's LinkedIn Live session, GPU Bursting, Scaling High-Performance Workloads on Demand. Whether you're joining us live or watching the replay, we're so glad you're here. This session is part of our LinkedIn Learning course focused on real-world cloud bursting practices for AI inference and high-performance workloads. And today's topic, GPU bursting, is especially critical for platform and DevOps engineers managing compute-intensive environments. We're joined by two incredible experts in this space. First, we have Dr. John Zhang, a GPU infrastructure specialist, who has spent over a decade helping organizations optimize their AI and ML compute environments across both on-prem and cloud architectures. And joining him is Prabhu Navali, co-founder of Avesha Systems. Prabhu has played a pivotal role in building Avesha's Elastic GPU service, an orchestration layer designed to make GPU resource management more dynamic, scalable, and cost-effective in Kubernetes environments. In this session, John and Prabhu will break down the fundamentals of GPU bursting, walk through real-world use cases like AI ML training, video rendering, and CAD simulations, and show you how to implement a GPU bursting architecture that fits your workload's budget and infrastructure. Let's get started. Over to you, John.
Okay, let's start with the fundamentals. GPU bursting is essentially the ability to temporarily scale your GPU resources to meet peak demand. Think of it like elastic computing, but specifically for GPU workloads. The key here is temporary. You're not permanently provisioning expensive GPU resources that might sit idle. Instead, you're dynamically scaling up when needed and scaling back down when the demand drops. This approach is becoming increasingly common in both cloud and hybrid environments. Why? Because GPU are expensive and most organizations can't afford to over-provision them. Now, let's talk about why GPU bursting matters to you as a platform engineer. There are four key benefits I want to highlight. First, cost efficiency. With a pay-as-you-go model, you're only paying for GPU resources when you actually use them. I've seen organizations cut their GPU costs by 40 to 60% using this approach. Second, escalating scalability. You can instantly scale up or down based on demand. No more waiting weeks for hardware procurement or dealing with capacity planning headaches. Third, performance. When you need to accelerate compute-heavy tasks, you have immediate access to powerful GPUs. This is crucial for time-sensitive workloads. And finally, flexibility. Use GPUs only when needed. This is perfect for workloads with variable demand patterns. Let's look at the architecture. GPU bursting typically involves three key components. First, you have hybrid or on-demand GPU bursting capabilities. This means you can burst from on-premise to cloud or between different cloud regions. Second, there's cloud and on-prem integration. Your bursting solution needs to seamlessly work across these environments, handling networking, security, and data movement. Third, you need orchestration tools. Whether you're using Kubernetes, Slurm, or other job schedulers, These tools manage the actual bursting process. The beauty of this architecture is that it's transparent to your end users. They submit jobs as usual, and the system handles the resources allocation behind the scenes. Now let's dive into real-world use cases. The first and perhaps most common is AI/ML training. The problem is clear. Training large models requires powerful GPUs, often multiple GPUs working in parallel. But these training jobs are typically sporadic. You might train a model intensively for a few days, then not need those resources for weeks. The solution: burst to cloud GPUs for faster training. For example, I worked with a team training transformer models on AWS. Instead of maintaining expensive on-premises GPU clusters that set idle 70% of the time, they burst to the cloud during training runs. They reduced their infrastructure costs by over 50% while actually improving training times due to access to newer GPU models. Inference presents a different challenge. While training is sporadic, inference can be unpredictable and have spikes. Consider a document processing system. During normal operations, you might process 1,000 documents per hour, but suddenly a large batch comes in, maybe 50,000 documents need processing immediately. With GPU bursting, you can handle these spikes without over-provisioning. I've seen companies use this for everything from real-time fraud detection to medical image analysis. The key is having that elastic capacity ready when you need it. Here's the scenario every data science team faces. Your data scientists need powerful GPUs for research and development, but equipping every workstation with high-end GPUs is prohibitively expensive. The solution is desktop to cloud bursting. Data scientists work on their local machines for development and testing, then burst to cloud GPUs for intensive computations. One financial services client I worked with gave their 50 data scientists access to cloud GPUs on demand. Instead of spending 50,000, 500,000 on workstation upgrades, they spend less than 100,000 annually on cloud GPU usage. And their scientists had access to more powerful GPUs than they could have afforded locally. Video rendering is another perfect use case for GPU bursting. VFX studios face extreme deadline pressure and highly variable workloads. Imagine a studio working on a film. They might have steady work for months, then suddenly need to render final 4K footage for transfer release, for trailer release. That's when they need 10x their normal GPU capacity, but only for a few days. GPU bursting makes this economically feasible. Studios can maintain a baseline of on-premises GPUs for daily work, then burst to the cloud for those critical deadlines. It's the difference between meeting deadlines and losing clients. Scientific computing presents unique challenges. Researchers running complex simulations, whether it's climate modeling, molecular dynamics, or astrophysics, need massive GPU power, but only occasionally. Universities and research institutions are perfect candidates for GPU bursting. They can share on-premises resources for routine work, then burst to HPC clusters with GPU nodes for intensive simulations. I've seen this enable research that simply wasn't possible before due to budget constraints. Researchers can now run simulations that would have required millions in infrastructure investment. Cloud gaming platforms face perhaps the most dynamic workload patterns. User demand can spike dramatically. Think about what happens when a popular new game releases or during evening game hours. Services like NVIDIA GeForce now use GPU bursting to handle these spikes. They maintain a baseline capacity for normal loads, then burst additional GPU instances during peak times. The economics are compelling. Instead of provisioning for peak load 24 by 7, they can scale dynamically, reducing costs while maintaining user experience. Finally, let's talk about engineering workloads. CAD and CAE applications are increasingly GPU accelerated, but engineering teams face the same challenge. Powerful GPUs are needed intermittently. An automotive design firm I worked with used GPU bursting for their simulation workloads. Engineers could run complex crash simulations and fluid dynamics models by bursting to cloud GPUs, completing in hours what would have taken days to on GPU only system. Now, let me hand it over to Prabhu, who will walk you through how to actually implement GPU bursting in your environment.
Thanks, John. Now let's get practical. When implementing GPU bursting, there are five critical considerations. First, sharing GPU resources from different clusters, on-prem and cloud, across teams, users, and jobs. This isn't about just technology. It's about governance. You need clear policies on who gets priority, resource quotas, and fair share algorithms. You need an unified allocation management framework. Second, dynamic allocation with priority and preemption. Your system needs to be able to handle job priorities intelligently. Critical production inference might preempt research workloads, for example. And don't forget idle timeout. GPU sitting unused even for minutes can be expensive. Third, capacity chasing across regions using spot and reserved instances. Cloud providers offer significant discounts on spot GPU instances. With proper checkpointing, other techniques, you can use these fault tolerant workloads and save 60 to 80% on compute costs. Fourth, auto scaling with orchestration. Your orchestration layer needs to understand GPU workloads. This means GPU-aware scheduling, automatic pod scaling, and node provisioning and intelligent node placement to get more utilization of the infrastructure. Finally, monitoring usage and avoid waste. You need a granular visibility into GPU utilization. I've seen organizations discover that 30% of their GPU time was wasted on idle resources. So let's look at the tools and the platforms that we would need for this, right? So let's talk about tools, right? So you have several options depending on your environment. For cloud providers, you have AWS, Azure, Google, all offer GPU instances with varying capabilities. Each has different GPU types, pricing models, and availability zones. In addition, neo cloud providers offer GPUs and advanced AI native operations. For orchestration and allocation, Kubernetes with the NVIDIA and AMD GPU operators are increasingly becoming popular. On top of these, Avesha Elastic GPU Service provides an effective GPU resource management platform across multiple clusters, supporting both NVIDIA and AMD GPUs. So platforms like EGS are vendor agnostic, cloud agnostic, and cluster agnostic. For bursting frameworks, you have options like EGS for Kubernetes workloads, or you can make HPC schedulers like Slurm work for the same bursting capabilities, but more and more workloads are moving towards Kubernetes, and EGS specifically addresses the multi-cluster, multi-cloud scenarios for Kubernetes workloads that we are discussing today. For monitoring, frameworks like EGS includes built-in monitoring. But you can also use Prometheus with GPU exporters and visualize in Grafana. The key is having a real-time visibility into utilizations, jobs, queues, and costs and the wastage. So let's look at some of the challenges, right? So GPU bursting is not a silver bullet for everything, right? There are challenges. So first challenge you would face is the data transfer latency. That's a real concern. If you have a model 50 gig, 70 gig, and your data is like, hundreds of gigs, transferring to cloud takes time. Solutions should include data caching, incremental transfers, strategic data placement. Look for frameworks like EGS that include predictive data movement capabilities, right? So that would help, positioning the data or moving the data in real time to help with the bursting. GPU instance availability can be problematic, especially for the GPU models like B200s and H200s. During ML conference deadlines, good luck finding an available B200. This is where multi-region, multi-cloud strategies and fallback options become critical. Software and hardware compatibility requires attention too. Different GPU generations have different capabilities. Different cloud clusters might have different tooling built on them, right? So you need a common framework, common orchestration framework that works across the clusters. That's a key. So you need something like an EGS, which is built ground up to handle orchestration across multiple clusters, multiple vendors, multiple cloud providers. Security and policies is another key concern, right? So a common policy framework across the clusters, whether they are in on-prem or a cloud, is a concern. And then we should look for frameworks like EGS that can bring common, normalized, strong security policies across the resources, across all the clusters. Observability, again, is another common framework challenge, right? So when you have clusters in the on-prem, clusters in the cloud, different regions, you would need a single deep observability framework is crucial. So look for solutions like EGS that have multi-cluster, deep GPU workload observability, GPU usage, wastage, and cost visualization from ground up. So let's see, we can check a scenario and then see how EGS solves the bursting use case, right? So let me walk through a real world scenario using EGS. Imagine a financial institution with one on-prem data center and one or more cloud presence, right? One on GPU cloud regions. It could be a neo cloud provider or a public cloud provider running multiple clusters. So one on-prem and one in region A and one in region B. So how does EGS handle this, right? So the whole bursting across these multiple clusters. So let's take a look at the reference model, right? So EGS is a platform for effective allocation and management of GPU resource. The slide shows the reference model. So EGS has a controller, right? So this is the brains of the operations of the management, right? So this can be deployed either in one of the worker cluster or in a separate controller cluster. So I think a separate cluster would be a preferred approach. The worker clusters, like the ones on the on-prem, where the GPUs are on-prem GPUs are there deployed, and cloud clusters, whether region A cluster, region B clusters, they're all registered with the EGS controller, and the controller manages the GPU inventory and allocation across all the clusters and all the workspaces. So workspaces are where the GPU workloads, like inference endpoints, are deployed. So workspaces are for users, groups, projects, the RAG pipelines, batch inferences. And workspaces would request, the users of the workspaces would request the GPUs and the GPU, and the EGS would allocate the GPUs, right? So when team A needs to deploy an inference endpoint, they specify their model and their preferences. Maybe they prefer on-prem cluster with the data locality and GPU type and the capacity, right? So EGS controller receives the request, could be via API or SDK or UI, and checks the inventory across all the clusters through the inventory manager. And if the preferred cluster is at capacity, let's say our on-prem is at full capacity, EGS automatically finds available resources elsewhere, perhaps in the cloud region. The beauty is this: it happens transparently. The EGS operator in the selected cluster handles the actual deployment, provisioning the GPUs, and setting up the inference endpoint. Teams get their resources without manual intervention, and the platform ensures optimal resource utilization across the entire infrastructure. So let's look at another scenario, right? So for the bursting scenario, this is another one that is becoming very popular, where you have a desktop to cloud bursting for data scientists. Data scientists work on their local environments with the AI PC that has some small GPU where they run their workloads, they've done some testing, but they need powerful GPUs occasionally, right? So through the EGS user self-service portal, they can request the resources with a few clicks. And EGS goes to work with the admin portal, gives platform teams control over policies, quotas, and approvals, and also ability to burst the desktop workloads to the available, wherever the capacity is available. This is the capacity chasing, whether it could be region A, region B, region C, depending on the type of the GPU they need. EGS goes to work and handles dynamic GPU allocation and capacity chasing. If on-demand instances are not available, it can automatically fall back to spot instances for non-critical workloads. So let's look at the detailed implementation flow for the bursting. Kind of covered this in the other slide, but I want to just go over this one more time. So the step one in the bursting starts with the request. Request initiation, a data science team, a RAG pipeline, or a user group, CI/CD pipeline submits a deployment request for their model. In this case, like data scientists request for a fraud detection model. They prefer an on-prem deployment, data locality, but prioritize availability over location. They need it immediately, right? So resource intelligence, right? Step two. So EGS automatically queries the inventory across all the locations, analyzes the current workload distribution and weightings, evaluates the data proximity requirements, and calculates the deployment cost for each option, and then decides where to place the where to place the GPU workloads. So the remember the workspace spans across all the clusters. So if I'm a team A, I have my workspace in an on-prem cluster. I have a workspace in the region E. I have a workspace in region B. Now EGS will decide where to place the workloads, where to give the GPUs, and so that we can deploy the inference endpoint. So the smart placement comes into picture. So the system determines that the on-prem cluster has a 3-hour wait time, but GPU Cloud Region 2 has an immediate B200 available at acceptable cost with a minimal data transfer overhead. It would allocate those GPUs for the workspace, for the request, and make that known to the operator that is running on that particular cluster. And this EGS operator in that cluster provisions the inference endpoint in the cloud cluster and automatically conferring the model with appropriate batching parameters and other model parameters, and even like in exposing the inference endpoint to the load balancers, so that the next step is to use the inference endpoint. So the fraud detection API endpoint becomes available within minutes, not hours, with the zero manual intervention. The entire flow happens automatically, freeing your platform team from constant resource management tasks. Yeah, I think again at this point I would want to bring John back and talk a little bit more about the future and where the busing is going.
Thanks, Prabhu. Looking ahead, GPU bursting technology is evolving rapidly. Let me share what's coming. Number one, GPU pooling and federated bursting will enable even more efficient resource utilization. Imagine GPUs being shared not just within your organization, but across a federation of trusted partners. Number two, distributed inference endpoints will span multiple clusters, automatically routing requests to available GPUs regardless of location. This provides better fault tolerance and latency optimization. Number three, AI-aware auto-scaling will understand your workload patterns and preemptively scale resources. The system will learn from your usage patterns and optimize resource allocation automatically. Number four, edge to cloud GPU orchestration will become critical as AI moves to the edge. You will be able to burst from edge devices to regional cloud seamlessly. Let's wrap up with key takeaways. GPU bursting enables flexibility and cost savings that simply aren't possible with traditional static provisioning. You get that resources you need when you need them without over provisioning. It's ideal for AI ML simulations, rendering, essentially any workload with variable GPU demand. If your GPU utilization is under 70%, you should seriously consider GPU bursting. Most importantly, this creates a future-ready architecture for dynamic workloads. As your needs evolve, your infrastructure can adapt without major overhauls. Prabhu.
Yeah, remember, successful GPU bursting isn't about technology. It's about processes, policies, and people. Start small, perhaps with a single use case, measure the results, and expand from there.
So thanks everyone for joining us today. GPU bursting is transforming how organizations handle compute-intensive workloads. And now you have the knowledge to implement it in your environment. Good luck with your GPU bursting journey.
What an exciting session on GPU bursting, scaling high-performance workloads on demand. We dove into how GPU bursting supercharges compute-intensive tasks with dynamic scaling, balancing performance, and cost. To schedule a GPU bursting assessment, contact us at info@avisha.io. Follow us for the next LinkedIn Live episode and keep pushing the boundaries of innovation. Thank you.